The overwhelming majority of computer vision systems used in anomaly detection today are built on convolutional architectures, especially convolutional neural networks, or CNNs. These systems rest on the assumption that anomalies can be discovered by scanning small image patches for visual irregularities, edges, corners, textures, then layering those patterns until something, quote unquote, looks wrong, right? In practice, this means applying filters across each image one location at a time, accumulating features in a strictly spatial sense. These filters are learned during training and respond to repeated patterns in the data. This is the heart of convolution. But despite their success in object recognition, these systems show deep limitations when faced with time-dependent, emergent, or physics-driven anomalies. CNNs treat each image as a separate, independent event. There's no memory of what came before. If an object subtly distorts over several frames, like a label warping under heat or a structure slowly bending, CNNs won't notice. They assume every image belongs to the same statistical world, even when that world is clearly changing. VOD corrects this by incorporating structured memory. It compares not just the present frame to a database, but the current state of transformation to its own history, capturing drift as it happens. CNNs also require massive labeled datasets to learn what is normal and what is not. Their goal is to minimize prediction error across examples they've seen, but in the real world, anomalies are rare. Many never appear in the training data. Worse, many are ambiguous, difficult even for humans to label consistently. This leads to the anomaly leakage problem, when the model cannot recognize new or emergent patterns as anomalous because it was never taught they exist. VAD avoids this entirely. It doesn't rely on class-based labels. Instead, it measures signal behavior, instability, disruption, and divergence from a baseline of physical regularity. Anomalies are defined not by class, but by how they behave over time. CNNs are fundamentally pattern matchers. They find correlations in spatial arrangements, but don't understand meaning. A specular highlight might be flagged as a defect. A faint crack might go unnoticed if it doesn't resemble the training data. CNNs lack awareness of signal origin, physical coupling, or causal dynamics. VAD replaces this spatial fixation with spectral structure. It analyzes images in the frequency domain, tracking how different regions oscillate, distort, or lose coherence. These harmonic vectors reflect the physical reality behind the image, not just the pixels in front of it. Where CNNs look at pixels, VAD encodes quantized harmonic signatures, mathematical fingerprints describing how regions behave, not just how they appear. Where CNNs detect difference by classification, VAD measures drift, the pattern of change from one moment to the next and across time. Where CNNs wait for something to resemble an error, VAD responds when change violates a domain-specific threshold. And where CNNs rely on categories, VAD uses semantic prompts built from phase instability, harmonic distortion, and spectral entropy, capturing meaning from behavior, not appearance.